Hello everyone, welcome to the second lecture of this course Microsensors and Nanosensors. In the first lecture we were discussing different type of sensors. We have classified sensors based on various parameters. So we have seen that this classification of sensors is really broad. Okay, so based on its properties, it can also be classified under various heads, like based on stimulus. We have seen the definition of stimulus, and which is similar to measurand in the previous class. So the sensors can again be divided based on stimulus, based on mean of detection, based on sensing material, and based on conversion phenomena. So in today's lecture, we'll try to understand these classification, and we'll move towards the fabrication of these sensors. So I will give you a basic concepts behind the fabrication of these sensors. So based on conversion phenomena, we can classify sensors under three heads: physical, chemical, and biological. Physical sensors are based on various conversions like thermoelectric, photoelectric, photomagnetic, etc. Similarly, chemical sensors are mostly based on chemical transformation, but there are certain sensors where we measure physical transformation. Similarly, electrochemical process is classified under chemical sensors. Similarly, for biological sensor, we have biochemical transformation and again physical transformation. Okay, there are other classifications like effect on test organisms and spectroscopy. We'll see some of them when we'll discuss the biosensors part. Based on stimulus, I can classify sensors under various heads like acoustic, biological, chemical, electrical, magnetic, mechanical, optical, thermal. Okay. There are other classes also like radiation. We are not going to cover all those things. Okay. Under acoustic sensors, we have measurement of wave amplitude, phase. We usually measure polarization and sometime group velocity of waves. Okay. Similarly, for biological sensors, we have various other stimulus like biomass identification, its concentration measurement, and its current state. Okay. Similarly, for chemical sensor, we have chemical transformation and other chemical phenomena, like we have given one example in the first lecture where we have seen what is a chemical sensor, where it was a two-step conversion. One was done by a transducer and there was a direct sensor installed. Okay, just after that. Similarly, electrical sensor have different stimulus. It can be measurement of simple charge, current, potential, electric field, conductivity, permittivity, etc. Okay. Similarly, magnetic sensors measure magnetic field, flux, and permeability. Okay. Mechanical sensors, the stimuli for mechanical sensors can be a simple position of an object, okay, its velocity, acceleration. We have seen that under classification that we have accelerometers. I have mentioned that we'll discuss characteristic of accelerometer in a separately, as compared to the existing sensors. Okay. Similarly, the stimuli can be simple force, pressure, vibration, viscosity, mass, and density. In the force sensor, we'll discuss some of them. Okay. Optical sensors can have stimuli in terms of wave amplitude, absorbance, reflection, refraction, and other aspects of optical, like scattering. Okay. Similarly, thermal sensors can have a stimulus of temperature, flux, conductivity, specific heat, etc. So all these stimuli are triggered by some physical or chemical or some biological phenomena. Okay, so these sensors will be capable of measuring all this. So in this course, we'll be covering some of these important sensors. Okay. Based on sensing materials, there are various classification like so this sensing material, please remember, are the receptor. Okay, so at the forefront where it sees the actual stimulus. Okay, so transducer and sensing material work in resonance. So sensing receptor actually receives the foreign particle or say foreign stimuli that it wants to measure, and transducer convert it into the electrical signal. Okay, so based on sensing material, we have a diverse class of material available which has been used as sensing material, like polymers. Okay, polymers were the initial class of materials that were investigated for sensing applications. Okay, the second class is metal oxides. Metal oxides are mostly wide band gap semiconductors, but we have other narrow band gap metal oxides also available, and it's composites with the metal oxides as well as with other materials like some metal nanoparticle or some polymer or some other class of material that we are going to discuss now. Okay, they constitute a major class of sensing material. Okay, with the inception of graphene, there are number of layered materials that has came into existence. Please note that when I am saying layered material, I mean to say that they exist in layers. Okay, layers means like I can have multiple layers of material, and mostly they are, say, this is material AB, this is material again AB, this is a monolayer of this material AB. They are either connected through some van der Waal force. You know that van der Waal forces are weak physical forces, or there can be some other forces between, or there can be some other bonding between all these materials. So if you see, these monolayers do exist. Okay, and if I can take out this monolayer from this bulk, okay, I can increase the surface to volume ratio. Okay, so for microsensors and nanosensors, this terminology surface to volume ratio is very important. Okay, we'll be using some of the property of these materials, the surface property of these materials in sensing. Please note that behavior of surface particle or surface atoms are different than the bulk material. Okay, because if, say, this is a material, okay, and if these are the surface atoms and these are the bulk atoms, the neighborhood of these bulk atoms are the similar atoms of this particular material, say AB. Okay, but the surface atoms, they seize all these external ambient. Okay, so the behavior of these surface atoms are different as compared to the bulk atoms. Okay, so in this course, microsensors and nanosensors, we will be mostly exploiting the surface property of these materials. Okay, similarly, heterostructure of these materials, be it layered material or metal oxides, are very crucial. Okay, so we'll see some heterostructure formation strategy in this course. Okay, otherwise you can also refer to some other good books where people has discussed heterostructure formation. Okay, nanotube of different materials are actually 1D structure of nanomaterial. So if I talk about nano particle, I can have 0D nanomaterial, I can have 1D, I can have 2D nanomaterials. When I say 0D nanomaterial, usually I am talking about, say, a quantum dot or say a nanoparticle. Okay, anything less than 20 nanometer. These dimensions are, please note that, can change. It's not a hard and fast rule that it should be less than 20 nanometer. Okay, but it is, I am telling you that it is around less than 20 nanometer, like 10 nanometer, 5 nanometer or something like that. Okay, but important thing is that the dimensions, the 3D behavior of this particle is chopped off. Okay, so there is a confinement of these particles in all these three directions. Okay, so I am calling it a 0D nanomaterial. Okay, so I was giving an example of nanotube. I told that nanotube is a 1D material. Okay, so this is, for example, a typical nanotube where this length can span anything from say 100 nanometer to say even some micron. Okay. However, these, I mean, the confinement, this tubes, the diameter is something less than 100 nanometer or so. Okay. This is a typical example of a nanotube. Okay. So the confinement is in two dimension. Okay. So only this nanostructure is in one dimension. So the growth is in one dimension. Okay. Similarly, for 2D structure, the confinement is through all this two dimension. So you have this kind of structure. So lateral dimension can be something, say the thickness is just 0.5 to say 2 to 10 nanometer, but lateral dimensions can be, you know, like some micron, and this dimension can also be say 100 nanometer to 500 nanometer or something like that. Okay. So these are 0D, 1D and 2D structures. When you have 3D confinement, you have 0D. When you have two dimension confined and growth only in one dimension, you have 1D structure, and when you have confinement only in one dimension, you have 2D nanosheet or nanoflake kind of structure. Okay. In this microsensors and nanosensors, we will be using all this kind of material in sensing. Okay. So then you have other kind of materials like materials having catalytic properties. Okay, like platinum and palladium, that kind of metals have catalytic properties. Okay. Similarly, for force sensors, piezoelectric materials plays very important role. So we'll see some of the important piezoelectric material. We know that naturally existing quartz has very good piezoelectric property, but we'll also see that there are some man-made piezoelectric material as well. Okay. So if you want to classify this based on material's nature, you can have either organic or inorganic material. Okay. If you want to classify them under the head of its conductivity, I can have conductors, semiconductors and insulators. For micro devices or microsensors, usually you use all. Okay, you need conductor, you need semiconductor, you need a insulator. Okay, let me give you a typical example so that this concept is clear. Say let's talk about a simple gas sensor. Okay, so if I have to define a gas sensor, please note that this gas sensor example I will be giving from lecture 2 to lecture 40th. Okay, or 60th, whatever will be the end lecture. Okay, so this example will take till last. Okay, so that you know, there is no diversity, and we stick to the same problem and we understand that with the same example. Okay, so a typical gas sensor is a device which can detect gases in trace level. Okay, these gases can be any toxic gas like SO2, NO2 or CO2, anything. Okay, a typical example of a gas sensor is say something like this. Okay, I mean, we'll discuss this in detail, but say this is a substrate. Okay, so this is a silicon substrate. Okay, this is a silicon substrate. On top of this, I have a oxide layer. Okay, so I have a oxide layer on top of this, which is a SiO2. Okay, on top of that, say I have a interdigitated electrode. Interdigitated electrodes are used to increase the current levels in these microsensors. Okay, so these electrodes are usually made up of say platinum or gold or any other metal, depending on the metal semiconductor junction, what it is forming. It is Schottky or it is ohmic. Usually we prefer ohmic contact. Okay, and on top of this, I have a receptor material. Okay, this receptor material can be any semiconducting material. Okay, it can be a metal oxide or a say other 2D material. Okay, 2D material like I can give an example of say transition metal dichalcogenides. Alright, this transition metal dichalcogenide, if you don't know, just have a look on internet what these materials are. Typically tungsten sulfide or moly sulfide makes a semiconducting transition metal dichalcogenide, but it can have a whole class of material. It can have insulating material, it can have conducting material. There are some semi metals in this class of materials. Okay, say I am typically coating this IDs or interdigitated electrode with say tungsten sulfide or say some metal oxide which is having a semiconducting property. So if you see this structure, I mean this is a typical structure of a gas sensor. Okay, a two terminal gas sensor. Will term it as a chemi-resistive. We'll discuss that in some time. But say this chemi-resistive device, if you see the structure, it has all the component. It has conductor, as I have mentioned that these IDs are made up of platinum or gold. Okay, so these are conductors. So in this structure I have conductors, right? Then if I see I have SiO2 in this picture. Okay, so which is basically a insulating oxide. Okay, so I have an insulator, and if you see my sensing material, the receptor itself is a semiconducting material. Okay, so I have a semiconductor. All right. So typically I have all this type of material existing in a sensor. Okay. Similarly, in other sensors also you will find that mostly it will use all kind of material. So we will see what are the typical materials that we use in the sensor, but for the time being we can classify these sensors based on material that it employs. Okay, I hope that this concept is clear to you. Okay, the application of sensors are really wide. Okay, it can cover anything from agriculture to a defense application. Okay, we'll understand this with some example. If I talk about agriculture land, okay, I can increase the crop production by measuring various parameters of the health of the soil as well as of the plant. Okay, so I can electrode based humidity sensor to measure the soil moisture content. I can also measure the nitrogen and other important contents of the soil, so that I know that if the soil is fertile or not. Okay, similarly for automotive, okay, if you are driving a car or if you are sitting in a public transport, you see around you there are number of sensors employed. Okay, consider a car. You are sitting in the car and your AC is working fine. Okay, and suddenly it starts showing on the screen that some particle level has increased or something. Okay, so why, I mean how it is able to show that? Because there are number of sensors that are working. Okay, this is just one example. Okay, it can employ number of sensors. For example, in the engine. Okay, how much diesel or petrol is going inside the engine, it is measured by flow meters. In the exhaust, what gases are being emitted are being measured by sensors employed near the exhaust. Okay, and apart from that, there are other sensors that are involved in this smooth operation of the car. Okay, similarly in the construction, distribution, domestic appliances, energy, power, health, medicine, everywhere you find its application. Okay, particularly rise with the Internet of Things, these sensors has gained much more importance. Okay, so I don't have to explain actually what are the application of these sensors. This application is really wide. Okay, and depending on your interest, you can choose any of these, and you can focus your research on that particular topic. Okay, so now since we have classified these sensors in various sense, we have understand different material that are employed in sensor. Okay, let's talk about sensors fabrication. Okay, as I have mentioned that mostly the sensors have a basic transducer and a receptor. Okay, so usually these receptors are coated or deposited on transducer. We'll learn different kind of deposition technique in this course in very nutshell, but for the time being, let's understand what is different ways to fabricate these transducers. Okay, there are various lithography techniques to manufacture or to fabricate the transducers. If you are not aware of lithography, no worries, I will give you a basic overview of lithography. Okay, then we have a very old technology known as LTCC, low temperature co-fired ceramic technology. They are also this technology is also being used very parallel to the MEMS technology for transducer fabrication. And with the rise of printing, flexible devices, several printing technologies has also emerged as a transducer fabrication technique. Okay, this printed sensor can be in the form of tattoos, in the form of sensors fabricated on paper, on textiles. Okay, so these there are various printing technology which do not need mask similar to lithography. Okay, so we'll see some basic steps of lithography in this course. Receptor material I have already talked about some time back, that metal oxides, 2D materials including graphene and beyond graphene 2D materials are very good receptor materials for various sensors. Maybe it's chemical sensor or force sensor or pressure sensors. Okay, then this deposition of these materials on transducer are very important. So usually in the laboratory, people test them by dropping say some microliter of this material if it is nano disperse. Okay, otherwise there are some physical and chemical vapor deposition techniques where you can actually control the thickness of the deposited film. Okay, and for various printing technology, again the suspensions of these liquids or which are prepared by various methods, maybe it's hydrothermal, sol gel or any other method, they are used for for fabrication of this receptor film. Okay, so this is a typical example of a microsensor. Okay, just have a look on this microsensor chip. Okay, if you see, there are various layers inside. So this area has various layers. Okay, say typically this is made up of silicon of thickness something say 5 micron or so. Okay, and it has been etched in this area. We'll see what is etching, but say this has been etched in this area, and this area has this different layers. So 1 2 3 4 5 layers. Okay, so this can be some insulating layer, this can be some heating layer. Okay, this can be again some insulating layer, this can be some metallic layer, and this can be a receptor. Okay, and the dimension of these are very crucial. Okay, say for example, this can be a nanometer thick film, this can be a micrometer gap IDs. Okay, this can be again a micron size this spiral kind of structure. Okay, on the right side I have given a scale so that you can understand that what level of thickness or what level of line width I am talking about. Okay, so I am talking something in this particular range. Okay, I am talking in this particular range, 1 micron to some few hundred nanometer. Okay, typically thickness of our hair is around 50 micron to 100 micron, and you can understand that with that context that in which region I am talking about. Okay, so fabrication of these layers as well as the complete chip is very crucial, and they are manufactured inside a clean ambient. So over the next few minutes, let's talk about some of the fabrication techniques that are utilized in fabricating such devices. Okay, this is a typical device that we fabricate regularly. This is a metal line. The brighter line that you are seeing are the platinum lines, and this is your the black line is showing some SiO2 part. Okay, so this has been patterned successfully on some wafer. Okay, we'll see what is a wafer and how this patterning can be achieved. Okay, so let us see what are the typical fabrication step of a microsensor. Okay, the first step in fabrication is wafer selection and its cleaning. Okay, so wafer is the main part on which our sensor is mounted, or on top of which you fabricate your sensor. Okay, so the same gas sensor example, if I give, okay, I have selected one wafer. Okay, however, just selecting a wafer is not, I mean, with just selection of the wafer, your job is not complete. You should know that how you have selected this wafer. Will it be compatible with the next processes that you are going to do on this wafer? Okay, and the most important part is its cleaning. Okay, so we'll see how to select a wafer and how to clean it. Okay, the subsequent step is photolithography. In this process, we are going to pattern the IDE that you have seen. Okay, I have just given one example of gas sensor in which I have told you that I have some IDE on this. Okay, so we'll see how to pattern these IDEs. Okay, or this is just one example. I mean, you can have your own structure depending on what device you are working upon. Okay, then the deposition. Okay, so I talked about sensing layer on top of this. So how this sensing layer is deposited? What are the deposition techniques available for this sensing in microelectronics? Okay, then at certain places we have to remove also. Here also there are certain parts that I have removed. However, you have just seen in this particular chip that the silicon has been etched, or the silicon has been removed, in which all these layers are placed. Okay, apart from deposition, removal is also very important. So we will learn what are the removal techniques that are available for the fabrication of these sensors. Okay, sometime we also need to oxidize certain part. So we'll see what is the oxidation technique that is available in microelectronics and nanoelectronics, particularly in the context of these sensors. Okay, we'll also learn the doping process. There are various ways by which I can dope my sensing layer, or even sometime my substrate. Okay, please note that doping is used to alter the electrical property of a semiconductor. Okay, say if I have a semiconductor, say X, okay, which is having say conductivity or say mobility of the electron in this is of say some value. Okay, now if I am doping it with certain kind of material, okay, certain kind of dopant, this properties, the electrical properties is going to change. Okay, so sometime we need to modulate these electrical properties of the film, okay, of the semiconducting film. Okay, so we'll learn what are the doping techniques. As you can see that mostly diffusion and ion implantation are used for doping. Ion implantation being very costly technique, mostly for sensors we deploy diffusion for doping. Okay, then comes the metallization. Metallization is very important because it helps in not only in making contacts, but it also help in other backend processes. Okay, then if you are doing this litho on complete wafer, you have to prepare your dies so that they can be taken out as a single chip. Okay, and then packaging of these dies. Okay, and finally when your die is prepared, it is electrically and mechanically tested. Okay, and at the end you have your final sensors chip. Okay, we'll learn some of these techniques in the coming time. Okay, we'll start with the wafer selection and its cleaning. Wafers are mostly classified under two heads: hard substrate and flexible substrates. Hard substrates are used for the conventional sensor that you have just seen, okay, a typical gas sensor or any other force sensor and all. Mostly the microelectronic industry, they rely on silicon as a substrate because it is compatible with the CMOS process, okay. However, there are other substrate that are that are being used, like quartzite, quartz, sapphire, and for high temperature application silicon carbide, okay. However, for flexible electronics or for flexible sensors, we have various flexible substrates, okay, like PET, polyimide, and others, okay. There are some substrate in this flexible substrate which are even stretchable, okay, like PDMS, okay. Then some sensors has to be fabricated on paper also, because for cost effectiveness and for other purposes, okay. Some wearable sensors comes on direct textiles. So textiles has also become very crucial flexible substrate in modern electronics, okay. So selecting this substrate on which you are going to fabricate your sensor is very, very crucial, okay. So you should know that which substrate you are going to use, what is the end application of your sensor, okay. Say for example, you need a sensor that has to be that someone has to wear, okay. You cannot go with the hard substrate, okay. Otherwise you have to make it on hard substrate and then transfer it to flexible substrate, which is again a costly process, and it's not that easy also, okay. So people are doing fabrication directly on flexible substrates, okay. So wafer selection is very, very crucial, okay. I will not talk about flexible substrate because this is a conventional course. Let us see how to choose a silicon wafer, okay. So if I talk about silicon wafer, they are grown as single crystals, okay. In this course I cannot discuss the wafer, how these wafers are grown, but please you can go and read some microelectronics book in which you can find that CZ method, which is known as Czochralski method, and float zone method are very popular methods to fabricate these wafers, okay. So they are grown as single crystals. From this single crystal, they are sliced from big ingots such that the flat surface is aligned along one of the several relative directions, which is known as orientation of these ingots, okay. The orientation is classified by Miller indices. Typically indices are denoted like this bracket. In bracket you have certain numbers like 100, 110, 111, 211. We'll see what are these indices if you are not aware of Miller indices, okay. And this orientation of your wafer is very, very crucial because this orientation affects the physical property of the silicon wafer, okay. So how these wafers are going to behave while etching, while doping, and how it is going to integrate with other material in subsequent step is very, very crucial, okay. Say if you have a material, say X, and if you want to deposit, say if its adhesion on say 111 wafer is very good, but you are deploying a 100 wafer, okay, it may not be that good as on 111, okay. So if you have the ability, you should always go with 111 over the 100 wafers, okay. So what I am talking about, like 111, 110, let's understand this, okay. So consider this axis x, y, and z, okay, and you have an intercept ABC, okay. Now say these intercepts are say 111, okay, or say 212, okay. So these planes are making some intercepts on this plane, okay. Now if I take inverse of this reciprocal of this, I have 1 1 1 or 1 by 2, 1 by 1 or 1 by 2. Okay. Miller indices are calculated by just you multiply the LCM of this with the reciprocals. Okay. So for 1 1 1 it is simply 1 1 1, while for 1 by 2 1 1 by 2 I have 1 2 and 1. Okay. So this is typical Miller indices for intercepts 1 1 1 and 2 1 1. Okay. Similarly, for other intercepts also you can find Miller indices. Okay. So this is very very crucial. I mean, Miller indices, why this Miller indices are used have certain stories. Okay, like say if a plane is parallel to say x and y plane. Okay, so you have intercept as infinity, infinity and 1, right? So it is, I am telling you that it is cutting say z axis at 1, and it is, this plane is parallel to x and y axis. Okay. So it is not making any intercept on x and y, it is only cutting the z axis. Okay. So you have intercept as infinity, infinity and 1. So the reciprocals you can find, and the Miller indices will be 0 0 1. Okay. So I mean, for mathematical calculation and all, these infinity terms will not be that convenient, and that's why we employ Miller indices. There are other reasons also behind using Miller indices. We will not go in detail of that, but you should know that these wafers comes in this 001, 110 and other ways. Okay. So once I understand the Miller indices, okay, I should also know that what are the choice of the wafers that are available to us. Okay. So Miller indices is very very important for to identify a silicon wafer. Okay. But apart from Miller indices, we have to classify these sensors, or we have to also say more things about these wafers. Then only we will be able to understand that what is the actual requirement. Okay. So usually these wafers are also divided based on what kind of doping it has. Okay. So either our silicon wafer can be N-type wafer, or it can be a P-type wafer. And with N-type, I can have say N-type wafer with having 100 orientation, or P-type wafer with 100 orientation, or N-type wafer with 0011 orientation, or something like that. Okay. So only Miller indices may not be sufficient to classify these wafers. Okay. So silicon wafer, I mean, this doping, as I have also mentioned earlier, that doping is nothing but it is introduction of some impurity knowingly to an intrinsic wafer. Okay, so that its electrical property or its electrical conductivity is modulated. Okay. Silicon can be doped as P-type or N-type. In the next lecture, we will see what type of dopants can be doped in a silicon wafer, in an intrinsic silicon wafer. Okay, and how this Miller indices can be combined with this dopants, so that the identification of these wafers become easier. Okay, thank you.